Have you ever wondered how your browser knows exactly which page to go back to when you hit back, or how a printer manages 50 distinct documents sent from 5 different computers without jamming the order? The answer lies in two of the most fundamental data structures in computer science: stacks and queues. Today, we are not just looking at diagrams, we are going to break down the logic, the memory management, importantly, the actual Java implementation code. By the end of this video, you will understand the LIFO versus FIFO are, how to implement these structures using both arrays and linked list, and the specific traps interviewers set for you. Let's dive in. First, we need to clear up a massive confusion. Beginners often mix up how data is stored with how it is accessed. Think of physical data structure like the container. This is your array, that is contiguous memory blocks, or your linked list, scattered memory nodes. Think of logical data structure like stacks and queues as the discipline or the rules we apply to those containers. You can build a stack using an array or using a linked list. The behavior remains the same, but the underlying mechanics change. We are going to build both today. Let's start with the stack, the golden rule. Here is LIFO, that is last in first out. Look at the diagram of bangles on a wrist. You physically cannot remove the blue bangle, the one you put on first, without removing the yellow one, the one you put on last. This is exactly how your browser history works. Visit Facebook, then Twitter, then LinkedIn. To get back to Facebook, you have to pop LinkedIn and Twitter off the stack first. In code, we care about three main methods. First one is push. This adds an element to the top. We must check for overflow here, meaning is the stack full. Second is pop. This removes and returns the top element. We must check for underflow here, meaning is the stack empty. And 3, pick. This just looks at the top element without removing it. Let's look at the code. This is a common interview question. Implement a stack using an array. We initialize a stack array and a variable top. Top starts at -1, indicating the stack is empty. For the push logic, first the safety check. If top equals capacity -1, if this is true, the stack is full, and we print stack full to avoid a crash. If we have a space, we increment top first, moving our pointer to the next empty index, and then insert the data. A stack of top equal to data. This operation is incredibly fast. Big O1 time. Now let's look at pop. We check if top is -1. If it is, the stack is empty and we return -1. If there is data, we retrieve it, then simply decrement the pointer, top minus. Crucial note, we don't physically delete the data from the array. It is still there in memory, but because we moved the top pointer down, it is logically deleted. The next push will simply overwrite it. The problem with arrays is fixed size. If we want dynamic size, we use a linked list. Here the head of the list acts as the top of the stack. In the code for push, we create a new node. We link new node dot next to the current head, and then update head equal to new node. This is also big O1, but with no risk of stack overflow unless your computer runs out of RAM. Quick pause to test your understanding. Trace this code mentally. Stack as is created. Push 5, push 8, then pop. Push 3, print pick. What is the number? It is 3 because 8 was removed and 3 was the last element pushed. Now let's switch discipline to the queue. The rule here is FIFO, first in, first out. Think of a ticket counter or a printer spool. You insert at the rear, last in, and remove from the front, first out. No cutting in line. Implementing a queue with an array is tricky. We track 2 pointers. front and rear. To add data, that is in queue, we check if rear has hit capacity. If not, we increment rear and place the data. To remove data, that is dequeue, we grab the item at queue from front and then increment front. There is a major flaw here. As we dequeue, front moves forward, leaving empty, unusable space at the start of the array. This is wasted space. This is why linked lists are often preferred for queue. They are efficient with no wasted space. We maintain a front pointer and a rear pointer. For in queue, create a new code. For in queue, create a new node. If the queue is empty, both front and rear point to this new node. Otherwise, we link the current rear to the new node and update rear to point to the new end. For dequeue, we take data from front, then we move front forward, front equal to front dot next. Here is the interview trap. Look at the edge case. If front becomes null, meaning the list is now empty, you must manually set rear to null also. If you forget this, you will have a dangling pointer. Let's summarize the showdown. Stack uses LIFO, think piles of plates or undo button. Queue uses FIFO, line for food or printer task. Before you go into an interview, remember these complexity cheats. All basic operations are big O1 times complexity. A space complexity is big O(n). Watch out for the red flags. Never call pop method without checking is empty and ask yourself the golden question. Do I need the latest data? If yes, use a stack. Do I need the oldest data? If yes, use a queue. That is the essence of stacks and queues. It is not just about memorizing code, it is about understanding the pointers and the data flow. If this deep dive helped you, hit the subscribe button for more data structure breaks down. Happy coding.